Okay, I think we have a few seconds maybe to start. We can wait. Okay, good afternoon. Are there any questions before we start? Okay, so the office hour will be here after the class, so you are welcome to stay and ask me questions. Yeah, go ahead.
Sorry, for the homework, what are you expecting for submission for the MATLAB?
Yeah, just print out your code and the plots.
Okay.
And handwritten part on explanations of whatever result you got. Yeah. Okay. So how many of you have class right after this class? Only one. Okay, all right. There is a reason that I asked, but it's not important now. It's usually what I have done in the past is I've given students more time to continue the exam, and that we do that if the room is free, and I'm happy that this room is free, so we could extend the exam time, but one of you has class right after this. We'll discuss that later on. Okay, so we are interested in computing the discrete Fourier transform DFT. And so if we want to compute the DFT of a time domain sequence xn, which is given by xk, so that's n equal to 0 to n minus 1 xn e to the power minus j 2 pi over n kn. Okay, so obviously this requires n complex multiplication. Well, in general, if x of n is complex signal, then it requires n complex multiplications, which is 4 times n real multiplications. And if we compute this for k equal to 0 to n minus 1, that would be n squared complex multiplications, right? So what the so-called FFT does, fast Fourier transform or the Cooley-Tukey algorithm, it reduces that from order of n squared to order of n log n. So FFT, fast Fourier transform, is not a transform. When we think about Fourier transform, it's not really a transform as such, but rather a fast way to compute. Fast means less number of multiplications. So it's a fast way to compute the discrete Fourier transform. Okay, so before we get started, let's take some very simple examples. So let's say that we want to compute the DFT of a 2-point sequence. So what would that be? So if n was 2, then xk will be equal to x0 first term, n equal to 0, e to power 0 is 1, plus next term, n equal to 1, x1, e to the power minus j 2 pi by n, that's 2 pi by 2 times k times n is 1, which is equal to x0 plus e to the power minus j pi is minus 1. So 2 cancels out, e to the power plus or minus j pi is minus 1. So then we can write that as x1 times minus 1 to the power k. So if I have a 2-point sequence A, B, the DFT of that is going to be cap A, cap B, which is going to be what? Is A plus B, so k is equal to 0, this is k equal to 0. So we get A plus B, and when the next point k equal to 1, minus 1 to power 1 is minus 1, and that's a minus b. So that's called the 2-point DFT. So if we have a, b, then you add a and b and you subtract, and that's the DFT. Cap A, which is a plus b, and the DFT second point is a minus b, and that particular configuration is called a butterfly. Okay. So we could continue with these kinds of examples, and let's say that I take a 3-point DFT. So what will be a 3-point DFT? So before we get to the Cooley to FFT, so let's say that we have, so xk is going to be x0 plus x1 times e to the power minus j 2 pi by n 2 pi by 3 times k times second term n is 1. So this term n is 1. This is n equal to 0. Plus n equal to 2 e to the power minus j 2 pi times n is to 4 pi k by 3. 4 pi k by 3. Okay, so that's the 3-point DFT. So for example, if we have 3-point sequence A, B, C, cap x0 is going to be A plus B plus C. So I can call that cap A. And then cap B, which is the next point, is going to be x1. Substitute k equal to 1. So that's going to be A plus x1, which is B. K is equal to 1. E to the power minus j 2 pi by 3 plus x2, which is C. K is equal to 1. E to the power minus j 4 pi by 3, which by the periodicity of complex exponential, this quantity here is same as e to the power plus j 2 pi by 3. So you just multiply by e to the power j 2 pi, which is 6 pi by 3 minus 4 pi by 3 is 2 pi by 3. So these two are conjugates, minus j 2 pi by 3 plus j 2 pi by 3. And C, which is x2, is going to be A plus B. Now k is equal to 2. So k is equal to 2. So that's going to be minus j 4 pi by 3, which I can then write as j 2 pi by 3. Okay, and then plus C. So if you substitute k equal to 2, minus j 8 pi by 3 is same as minus j 2 pi by 3. Okay, so I will stop here. There is a little more simplification that we can do, but that I will leave to your homework to play with, and but we'll stop here with that. So that's the basic 3-point DFT, and you can see that really it requires multiplication by this complex exponential, which is cosine 2 pi by 3, cosine 2 pi by 3, which is minus root minus half. Is it minus half? Cosine 60, which is sine 30, yeah. Plus j sine 2 pi by 3, which is same as cosine 30. So minus half really isn't a multiplication. You can shift right by 1 bit. So ultimately this whole 3-point DFT will involve 2 multiplications by root 3 by 2. Okay, that's kind of part of your homework. You will play with that. I will leave it at that. So what about 4-point? What about 4-point DFT? So we have xk is equal to x0. If I just substitute here x0, by the way, e to the power minus j 2 pi by n, e to the power minus j 2 pi by 4 is going to be e to the power minus j pi by 2, which is same as minus j, not same as minus j. Okay, so x0 plus x1 times minus j to the power k. So n is equal to 1, so k times 1 is k, plus x2 minus j to the power n is equal to 2, 2k, minus j to the power 2k, which is minus j squared raised to the power k, which is minus j squared is same as j squared, which is minus 1 to the power k. So that's x2 times minus 1 to the power k. And the last term x3, what happens when n is equal to 3? That becomes e to the power, or this minus j to the power 3k. Minus j to the power 3k is equal to minus j times minus j whole squared. That's minus j to the power 3, all raised to the power k. And this quantity we already know is minus 1. So minus j times minus 1 is plus j. So that's simply j to the power k. So x3 times j to the power k. Okay, so then I can write down these quantities. Let's say that we are computing cap x0, 1, 2, 3. So this is going to be, if I am computing these 4 points, so this is, let's call it cap A, B, C, D. So this is going to be, if k is equal to 0, this is k is all of these, to the power 0 is 1, so that's just A plus B plus C plus D. If k is equal to 1, then what happens? That's A, minus j to power 1 is minus j, B, minus j raised to the power 2 is minus 1, and minus j, excuse me, I am a little lost here. Yeah, so k is equal to 1, minus 1 to the power 1 is minus 1, yeah. And then j to the power 1 is j, so plus d, okay. Then I substitute k equal to 2, so that's A minus B, A minus B, minus j squared is minus 1, minus 1 to power 2 is plus 1 plus C, and then j squared is minus 1, okay, and then x is k equal to 3, minus j to the power 3, we just saw, this was plus j, minus 1 cube is minus 1, and j cube is minus j. Okay, so these are the equations for the 4-point DFT. I can describe this by a matrix . Okay, so the first term, first row and first column are always 1. Okay. Why is that? Because the first column n equal to 0, e to the power 0 is 1. First row k equal to 0, e to the power 0 is 1. Okay, so B is A minus JB minus C plus D. C is minus B plus C minus D, and then JB minus C minus D. Okay. Okay. So at least you can see that all of that has no multiplications by any numbers. So the 4-point DFT, there is multiplication by J, which is not really a multiplication. J times some complex number A plus JB is simply going to swap the real part and the imaginary part. So the imaginary part B becomes the real part with a negative sign minus B. The real part here, A, becomes the imaginary part after multiplying by J. So multiplying by J or minus J are not real multiplications. So we can see that there aren't real multiplications involved. But what is a quick way to see how we can describe this by using the butterflies? Well, let's try to take a look without going through the systematic way of the Cooley-Tukey algorithm. So I can see that I see these terms A plus C and A minus C. Well, that's a butterfly operation. So if I just start with A, C and have a butterfly, so that's A plus C and A minus C. And we see same thing here, B plus D, and well, there is minus B plus D, which is, something went wrong here. There should have been a J here that I missed. Okay, I missed a J. So if you take the J outside the bracket, minus J outside the bracket, that becomes B minus D. So there is B plus D and B minus D. So if we start with these two, and we have B plus D and B minus D, and then what we do see is the B minus D. So if you look at this one here, so let's write this. Okay, let's write this as this is equal to A plus C plus B plus D. This is equal to A minus C minus J times B minus D. This is A plus C minus B plus D, and this is A minus C plus J times B minus D. Okay, we have these quantities A plus C, B plus D, A minus C, B minus D. And so if you look at this quantity and this quantity, that's just another butterfly. Some number plus another number, some number minus another number. So that's just another butterfly, and that's cap A, and that is cap C. Okay, so what is happening with the other two? Let's take a look. A minus C minus J B minus D. So what I can do is multiply this quantity by minus J. Okay, I multiplied this quantity by minus J. Okay, then what happens? So I have minus J times B minus D. So then the A minus C plus that and A minus C minus that, minus minus J becomes plus J. So that is the 4-point DFT computed using only 2-point DFTs or butterflies. And as we will see in a couple of minutes, that this multiplication that we had to perform minus j will be called a twiddle factor, which are complex exponentials. So in this case, it so happens that the W, the twiddle factor W, which is e to the power minus j 2 pi by n, in this example happens to be minus j. So that would be simply called W in general, but yeah. So n is equal to 4, so this is 1 at an angle minus 90 degrees, which is minus j. Okay, so these examples illustrate how the butterfly is used to compute any large point FFT. So let's just jump into the Cooley-Tukey algorithm. So the basic idea is to take a large problem and divide into two smaller problems, the divide and conquer problem. And there are many classes of problems that perform divide and conquer. So the basic idea is to express an n-point DFT in terms of 2 n by 2 point DFTs. So if I can express any n-point DFT using 2 n by 2 point DFTs, then, well, if I had to compute a 1024 point DFT, then I can express that to 512. 512 can be expressed as 256. That can be in terms of 128 down to 64, 32, 16. And you go that many steps, you go log n steps to get to 2-point DFTs. Okay, so there are two approaches. So the so-called Cooley-Tukey algorithm has two versions of that: decimation in time and decimation in frequency. Okay, so DIT and DIF are two approaches, two dual approaches. We can think of them as dual approaches. Okay, so let's start with the decimation in time. So what is really the difference between DIT and DIF? So the way that okay, so let's just explain the basic idea of what is the meaning of decimation in time. So if I have samples 0, 1, 2, 3, let's say a 8-point sequence. So first thing you downsample and separate in terms of even and odd. So these will be sample number 0, 2, 4, 6. These will be 1, 3, 5, 7. Okay, so that's how I describe the 8-point in terms of 2, 4-point. And then if I want to go through this process one more step, so describe this as even of the even and odd of the even, then this will be 0 and 4, this will be 2 and 6. And if I take the odd sequence, again describe that as even of the odd and odd of the odd, this would be 1 and 5 and 3 and 7. So ultimately, in a decimation in time DFT, the inputs are given to the 8-point DIT in that order: 0, 4, 2, 6, 1, 5, 3, 7. And we say that the time domain samples are in decimated order and the frequency domain samples are in order. So this will be cap x0, cap x1, 2, 3, 4, 5, 6, 7. And that's called, so anytime we see inputs and outputs ordered like that, that's called a decimation in time. But as we will see that these things really are somewhat meaningless, but anyway, this is the origin. This is the origin of how it started. What happens in decimation and frequency, instead of downsampling the time domain sequence, the frequency domain computation is done in a way that we will compute the even coefficients and odd coefficients. So the DIF will have the time domain samples in order 0, 1, 2, 3, 4, 5, 6, 7. And the frequency domain outputs will be in that decimated order. So we'll get to that. Okay, so that would be the DIF. So the DIT FFT, we are trying to compute xk is summed over all n, xn e to the power minus j 2 pi over n kn. So what's the first goal? The first goal is to express xn, divide xn, not express, divide xn in terms of this sample is called xn. So the even samples would be called something like, I could call them as x2n, there is nothing wrong with that, but let me call them as x2r. Well, I don't see anything wrong. I could call that as 2n, okay. There's nothing wrong. And then I could call the odd as x2n plus 1. Okay. So we are trying to express xn using x2n and 2n plus 1. So this is equal to summed over n equal to 0 to now n by 2 minus 1 x2n e to the power minus j 2 pi over n k 2n. Okay, think about what I'm saying here. So this, when substitute n equal to 0, 1, etc. So these will be sample numbers 0, n equal to 1, 2 times 1, 2 times 2, etc. So this, so I've replaced n by 2n to get, I could have used 2r or 2l or something. It doesn't really matter. And then replace this n by 2n to only capture the even samples. So this sum is now going to be two different sums, one containing the even samples and another containing the odd samples. Okay, so the second sum that contains the sample numbers 1, 3, 5, 7, etc. So this is the even samples and this is the odd sample. That's what is called decimation in time. And you can see that the corresponding coefficient here, these odd samples, n has been replaced by 2n plus 1. So these are the odd samples. Okay, so if you look at the index of the sum, so if I had 100 quantities to add, the summing index now will have 50 quantities to add in the even part, 50 quantities to add in the odd part. So the sum now, instead of 0 to n minus 1, is 0 to n by 2 minus 1. So the last sample number, the very last sample number, when you substitute that here, 2 times n by 2 minus 1, so this will be 0 to up to n minus 2. So the last index of the input will be xn minus 2. 2 cancels out with this, we get n, 2 times 1 is minus 2. And the very last one here will be same thing plus 1, so up to n minus 1. So that's what is the whole index now. If you think of it in terms of the original index, that was 0 to n minus 1 of the sample index. Okay, so that's the decimation in time. And then if we look at so this quantity here can be written as e to the power minus j 2 pi by n k times 2n multiplied by e to the power minus j twice pi over n k. Okay, so something to the power a plus b is something to power a times something to power b. Okay, and then so what else can we do? So this 2 can be brought to the denominator and can be written as n by 2. And same way these 2 can be brought to the denominator and can be written as n by 2. Okay, so now what we have here is, so what do you think this first term is? Sum n by 2 samples times e to the power j twice pi by the number n. N is now n by 2 because we have n by 2 samples. Kn. Yes, very good. So I can write that as gk, where gk is the, well, I can start with, let's say gn is equal to x2n, which is the even sample. So this is n by 2 points, and odd sample I can call hn is equal to x2n plus 1, and gk is the DFT, n by 2 point DFT of gn. Okay, so we take the n by 2. So this first sum is nothing but n by 2 point DFT of the even samples. Okay, e to the power minus j 2 pi over nk does not depend upon the summing index n, and that quantity can come outside the sum. So I can write that as plus w to power k, w is e to power minus j 2 pi by n, times hk, where hk is the n by 2 point DFT of hn, or the odd samples. So now in fact we have expressed the n by 2, the n point DFT. We are not quite done, but we are almost there. N point DFT of xn can be expressed as 2 n by 2 point DFTs, n by 2 point DFT of the even samples and of the odd samples. Why is it that we aren't done? Because this whole equation, gk, the index of k in this equation is from 0 to n by 2 minus 1. So we have exactly described the first n by 2 point DFT of xk for k equal to 0 to n by 2 minus 1. Okay, how do I describe the next n by 2 point DFTs, that is x n by 2 through n minus 1? And so, by the way, the DFTs are periodic. I didn't go into theory of that, but these are periodic even by the complex exponential periodicity. By the mathematical expression, these are periodic with period n. So xk is periodic with period n. Gk and hk are periodic with period n by 2. So if I am going to compute for k equal to n by 2 plus 1 up to n minus 1 xk is going to be, so let's think about k is equal to n by 2 plus 3 as an example. So if k is equal to n by 2 plus 3, then what will be g n by 2 plus 3? Same as g3, because that's periodic with period n by 2. So that means whether I add or subtract n by 2, it doesn't really matter. So that will be, well, I could say, I could write it in another way. I think what may be more useful, okay, it may be more useful. Not that it's wrong, it's not wrong. So I could write it as x, okay, so then I have to keep it as 0 to n by 2 minus 1. Well, okay, let's still do that, So x, so k equal to 0, 1, up to n by 2 minus 1, x k plus n by 2 is going to be g k plus n by 2 plus e to the power minus j 2 pi over n k. Now k is now replaced by k plus n by 2, h k plus n by 2. Okay, so from that equation that we had, from the same equation, from that equation here, we are only substituting. So this will help us. If k is equal to 0, then I get x n by 2. And if k is n by 2 minus 1, I get k n by 2 plus n by 2 minus 1, n minus 1. Now because of the periodicity of g and h, these two really don't matter. Gk plus n by 2 is the same as gk. Now what about this product here? I replaced k by n, k plus n by 2. So e to the power minus j 2 pi by n k times e to the power minus j 2 pi by n times n by 2. N cancels out, 2 cancels out, e to the power minus j is minus 1. So that quantity is minus 1. So this quantity then becomes gk minus, so this is minus 1, w to power k, that's w to power k is k. So if we have x2n of length n by 2, x2n plus 1 of length n by 2, and we compute n by 2 point DFT. Okay, and then we basically, so the last part is to merge these two. And so that merging these two, so this is a gk and hk. So multiply these by a twiddle factor, w to power k, and then have a large merging for the butterfly, and this merging is nothing but n by 2 butterfly operations, and that would be the end point DFT of xk, and that is the high level block diagram, and these will be the twiddle factors. Okay, so now in fact we can take this n by 2, express that as 2n by 4 point DFTs, and same here, and keep moving, and we'll see that ultimately we'll get to the butterfly structure that we need. So I have some diagrams printed out from the Oppenheim Schaeffer textbook, the one we use for the DSP class. So that is the decimation in time block diagram of 8-point DFT. So if you look at what I just did, think about what I just did. Oh, okay, so I should say okay, that's the 4-point, that's another 4-point DFT. So this WK, so if you think about this quantity as G0, G1, G2, G3, and these outputs as H0, H1, H2, H3, then for k equal to 0, x0 is going to be G0 plus W to power 0, H0. X1 is G1 plus W to power 1, H1, and that's this two factor W to power 1 right here. And this is a G2 plus W squared H2, and that's why the second one from H was multiplied by W squared, and this is a G3 plus W to power 3 H3, and the last one is multiplied by W cube. And for the last half, this will simply be minus, so that's G0 minus W to power 0 H0. This is G1 minus W H1. This is G2 minus W squared H2. And this is G3 minus W cube H3. And if you look at these corresponding operations, G0 plus W to power 0, H0 and minus, and that is simply the first output from here and first output from here and the butterfly of that. Same with the next one, G1 plus, G1 minus, these two are the next butterfly. And so there are n by 2 butterflies to merge. So the way to merge is this twiddle factors plus n by 2 butterfly operations. Okay, so if we indeed continued decomposing that 4-point to 2-point, then we would have this diagram here. So this is 2-point of the even, odd of the even 2-point, and then what you see are the twiddle factors Wn and Wn squared, okay, and then the merging is 2 butterflies, same here. Now one thing you will notice is this diagram is exactly same as the one I had drawn a few minutes ago, the 4-point butterfly that I had drawn before by just observing and taking common things out is exactly same, and that minus j that you see here is shown as W squared. So if you indeed compute W squared in this example, e to the power minus j 2 pi by 8 whole squared, that's going to be e to the power minus j 4 pi by 8, which is minus j. That's e to the power minus j pi by 2, which is minus j. So that's why it's shown as W squared. So one thing to notice is that this thing here, what is shown as W squared, should really be written as W to power 1, but that W is Wn by 2 power 1. Wn by 2 means e to the power minus j 2 pi over n by 2 raised to the power 1 is the same as Wn squared. So that's kind of a general property. So W n by 2 is equal to Wn squared. 1. So this is e to the power minus j 2 pi over n by 2, which is e to the power minus j 2 pi over n times 2, and that is wn. This is wn squared, e to the power minus j 2 pi by n whole squared, and that is equal to wn. So that quantity is wn. Okay, so that's why it's shown as instead of w to power 1, which is indeed w to power 1 with the quantity n by 2, the length of the sequence. And with respect to scaled up to the original length, that becomes squared. So that's called the decimation in time. Any questions? Okay, so now we can talk about decimation and frequency. So the main idea here is, instead of expressing the original sum xk in terms of two different sums, instead of expressing that as two different sums, here we explicitly compute the even and odd coefficients. So let's start with the even DFT coefficients. And then we will compute the odd DFT coefficients, x2r plus 1. So xk is summed over all n, xn e to the power minus j 2 pi over n kn, and we replace k by 2r. So x2r is equal to n equal to 0 to n minus 1, xn e to the power minus j 2 pi by n k times 2r. Okay. So x2r is computing the even coefficients, and x2r plus 1 will compute the odd coefficients. And in this case, the inputs are in order. Inputs are 0, 1, 2, 3, 4, 5, 6, 7. So we are going to describe the sum again as two different sums. But in this case, the sum of the first n by 2 and next n by 2. So the order of the sequences in the time domain is in order. So that quantity can be written as, so the next 2r is equal to n equal to 0 to n by 2 minus 1 xn e to the power minus j 2 pi by n k 2r plus n is equal to n by 2 to n minus 1 xn e to the power minus j 2 pi by n k 2r. Okay, so we have divided the sum into two different groups. The first group has all the n by 2 samples, first n by 2 samples. And this group has the next n by 2 samples. And the next goal is to bring these two summing indices to the same range. And we can do that by replacing n minus m cap n by 2 as m. Okay, if I do that, then this sum becomes m equal to 0 to n by 2 minus 1. And n becomes m plus n by 2. So this is x m plus n by 2. Okay, let's see. E to the power minus j 2 pi by n. Something has gone wrong, right? Yes. Yes, that's what I notice now. So k is replaced by 2r, the n stays. Thank you. Yeah. So k stays as 2r, and then that n stays here. Yeah. N. Okay. So k stays as 2r. We replaced k by 2r. And then n, I was looking for where to replace this n, and I didn't find it. So obviously there was a mistake. So that n now, n is going to be replaced as m plus n by 2. Okay. Yeah. Okay, so now let's see. This quantity again, we can write that as e to the power minus j 2 pi by n 2rm times e to the power minus j twice pi over n 2r n by 2. Okay, so we take that and express that as two products, and let us see what happens. N cancels out, 2 cancels out, e to the power minus j to pi r is simply 1. So that's complex exponential with r rotations around the unit circle clockwise. Okay, it doesn't matter if you take clockwise or anti-clockwise. Okay, so now what I have, so now this whole thing here, this whole thing is just that. So I can write this quantity is equal to, so now m is simply a dummy index, and I can put that m back to n. It's just a dummy index, it doesn't matter. So if I change this m to n, change this m to n, and this m to n, nothing really changes. So I can now write that whole thing as summed over n equal to 0 to n by 2 minus 1 xn plus xn plus n by 2 taken outside a bracket e to the power minus j twice pi over n to r. Okay, and then that 2 can be written in the denominator as n by 2. Okay, so what we see here is this is the n by 2 point DFT of xn plus n by 2. Any questions so far? So the algebra becomes a little bit more cumbersome, but not too much with 2r plus 1. Okay, so let's continue with that quantity. So x 2r plus 1 is equal to summed over n equal to 0 to n minus 1 xn. Yeah, I had a mistake here, continued from this line. K is here and continued from here. Okay. So we just replace k by 2r plus 1. The n stays, k becomes 2r plus 1. So xn e to the power minus j twice pi over n 2r plus 1. Okay, so that can be written as n equal to 0 to n by 2 minus 1 xn e to the power minus j twice pi over n times 2r plus 1 plus n equal to n by 2 to n minus 1 xn e to the power minus j twice pi over n times 2r plus 1. Okay, so we go through the same process. N is equal to n minus n by 2 is equal to m. N is equal to m plus n by 2. And if we do that, n minus this n by 2 minus n by 2, this becomes m equal to 0. And that's n by 2 minus 1. This and this n become m plus n by 2 and m plus n by 2. Okay, so let's try to work on that part. So e to the power minus j twice pi over n times m plus n by 2 times 2r plus 1 will be e to the power minus j twice pi over n times m times 2r plus 1 times e to the power minus j twice pi over n times n by 2 times 2r plus 1. Okay, so we just write this as m times that quantity and then n by 2 times that quantity. N cancelled out, 2 cancelled out. This 2r plus 1 is an odd number, and any complex exponential with odd pi is going to line up in this axis here, which is minus 1, opposite side of the real axis, right? So this is minus 1. So this is minus 1. So finally we can write, let's see, so this one I can write as n equal to 0 to n by 2 minus 1. So again, because of the dummy index, I can put this m, and this m as n. It's a dummy index. So then what we see is xn, and there's a minus sign here, that minus 1. So we have xn minus xn plus n by 2, that m is dummy n, times e to the power, that quantity there, which is minus j 2 pi n, times 1 multiplied by e to the power minus j twice pi n 2r. Okay, so I've now described this as product of two things, and then that 2 can come to the denominator and become n by 2, and if you look at this whole thing is the n by 2 point DFT of that whole thing. Okay, so this is the n by 2 point DFT. The odd samples are the n by 2 point DFT of this quantity. And really, if you look at what we are saying, that the even part is the n by 2 point DFT of this plus that, and then the odd part is the n by 2 point DFT of this minus that times that. So what does that really mean? It simply means that I can compute this plus that and this minus that by n by 2 butterflies. And then to this part I can multiply by this, something went wrong, I should have a k here, or r, something got missed here, let's see here, e to the power n should be missing, right? Yeah, this m is here, n is here. So yeah, so we multiply this, so we do the butterfly of xn and xn plus n by 2, compute this and that, and to the bottom part we multiply by the w to power n, and then compute the DFTs of this part and this part. So let me just show you at a high level what it looks like. So we have xn, which are n by 2 samples, first n by 2 samples, xn plus n by 2, which are next n by 2 samples. And then you do a butterfly of that, this whole large butterfly. By the way, butterfly is -1 here. Okay, and then we multiply these by w to power n. So that multiplying by w to power n, when n things come out, multiply by w to power 0, w to power 1, w to power 2, etc. and go down. Okay, then the n by 2 point DFT will lead to x2r plus 1, and that's of length n by 2, and then compute the n by 2 point DFT, and that will be the even DFT, it's x2r. So that is the decimation and frequency. And if I can show you what that one looks like, okay. So the 8-point decimation and frequency, if you look at this one here, is this the correct one? Okay, so let's look at this one. Yeah. So n is 8, so we take the first half samples, the next half samples, butterfly of 0 and 4, 1 and 5, 2 and 6, 3 and 7. These are the w to power n. So think of this and this as n equal to 0. This is n equal to 1. Okay, w to power 0, 1, 2, 3. And then whatever you see to the right, let's see here. So this whole thing and this whole thing is the 4-point DFT, and this is the 4-point DFT. Okay, so that's basically the decimation and frequency decomposition. But then what we see here, so from the 4-point, the okay, so if you look at this 4-point here, these are again the butterflies of the so these are, so you can think about this as n equal to 0 and 1 if you like, n equal to 0 and 1 if you like, and then do the butterflies, and then the 2-point DFT, which is this here, and then this I explained why instead of this is w to power n is 1, but instead of writing this as w to power w4 to the power 1, it's written as with respect to the original n, w8 squared. And if you keep going through that process, that's what this finally is. Okay, so we have spent a lot of time talking about the Cooley-Tukey decimation and time and decimation and frequency algorithms, but many of these are really equivalent. You know, there wasn't really a reason or a need to derive this from the decomposing the odd and even, we could get to that very quickly by simply transposing. If you take the 8-point decimation in time, okay, if you take this one here and just transpose that, so just reverse the directions of the edges, and then you will get back the decimation and frequency. So let's talk about that, why it is possible to transpose. So let's now talk about what exactly, if I have an n-point DFT and I want to express that as a matrix, cap x0 through cap xn minus 1 can be written as the DFT matrix times the time domain samples Okay, so if you think about k equal to 0, this line k equal to 0, so these all will be 1. And as I explained, this line n is equal to 0, so these will be all 1. So let's talk about k equal to 1. So k equal to 1, so this is w to power kn. K is equal to 1, so this line k is equal to 1, n equal to 0, n equal to 1, so that's why it's w, k equal to 1, n is equal to 2, etc. And the next line, k is 2, w squared, k is 2, n is 2, w fourth, k is 2, n is 3, w to the power 6, w cube, 3 times 2, 6, 3 times 3, 9, and so on. So that's what is the DFT matrix. So if you look at in each first column, w squared, w cube, etc. Second column, w squared, w fourth, 6, 3, 6, 9, etc. And so when you see, let's call this matrix B, so x is equal to B times lowercase x, these are vectors, yeah. You can see that I can write this also as B transpose X, because the DFT matrix is a symmetric matrix. So the B quantity is, B matrix is the transpose of itself. So if I just transpose the structure, then I get a V transpose, that would still be the same DFT matrix. Okay, so what is, let's just briefly talk about this whole idea of transposition. So if I have, let's say we have some A, B, or let's say Y 0, Y1 is equal to A, B, B, C. This is symmetric x0, x1. Okay, so this is x0, x1, x0 times A plus x1 times B is y0. Y1 is B times x0 plus C times x1 is y1. Okay, because this matrix is symmetric, and then that says that if I just transposed, so these outputs become inputs, these arrows go that way, this arrow goes that way, this arrow goes that way, this arrow goes that way, these inputs become outputs. Then the computation will remain intact. So if you look at, if I replace this by x0, x1 and call this y0, y1, you can see that y0 is x0 times A plus this was x1 times B. y1 is x0 times B coming this way plus x1 times c. So we did not alter the computation by transposing and getting a different structure. And that's why this transpose operation maintains the input-output properties of multi-input, multi-output system only if that matrix is symmetric, which happens to be the case in the DFT matrix. So because the DFT matrix is symmetric, we can simply transpose any FFT structure to get a different looking structure, but should still be computing the DFT, same DFT. So any DFT structure can be transposed to get a different structure that computes the same thing. So in your homework, you will play with how to start with the 8-point DIT and then transpose that to get the DIF. I'm not doing that in class, but that's part of your homework for next week. I'll post the homework on Wednesday. So there are a couple of ideas that I want to talk about before we stop today. So the way that you have to transpose before you transpose, let me see. Okay, so let me see. Yeah, so this was the original. This is DFT. Okay, I believe no, that's not DFT. Okay, anyway, I will mention a little later, maybe in the next class, but we'll get to that. So there are a couple of ideas that I wanted to briefly mention before we stop. So how can we compute? So xk is summed over all n and so what? That's the DFT. The IDFT xn is 1 over n summed over k xk e to the power plus j2 pi over nk. So what does that suggest? So take any FFT structure, conjugate the twiddles. So conjugate these twiddle factors, whatever was minus, make it plus, and scale by 1 by n, and that becomes IFFT. So any FFT structure with conjugated twiddles and scaled at the end by 1 by n, n is a power of 2, so usually that doesn't mean a multiplication. Okay, so IFFT structure. So again, you will get a little experience with this in the next homework. So if I describe in matrix form, X was V times lowercase x, and X is going to be B inverse, that's the IDFT matrix, times cap X, and that is going to be 1 over n times B conjugate cap X. So that's in the matrix form. So whatever we were, all that we are doing is that DFT matrix that I had shown using the twiddle factors, you just conjugate all of those. So all these things are conjugated. And then a scale factor of 1 by n, then that becomes the IDFT. Okay, that's briefly about IDFT or IFFT. There was one more small idea that I wanted to talk about. What do you call it? Yes, twiddle factors. Twiddle shifting. Let me just mention one small idea, then we will stop. This so-called twiddle shifting. So if we have something like this, and let's say that we have some twiddles w to power a and b, and this is equivalent to shifting a twiddle w to power c outside. So if I move w to power c to the right, this becomes w to power a minus c, b minus c, and to the right we have c. That's called the twiddle shifting properties. This is another way to get equivalent DFTs, and I'll talk a little more maybe next class. But in the homework, you can see that by applying the twiddle shifting, we can also describe the equivalence between DIT and DIF FFTs simply by using the twiddle shifting properties. So that's kind of part of next homework. So I will stop here today. I think there was one question from somebody 30 seconds ago. I heard a sound. No? Okay, I'll stop here and we will continue this topic next class. I'll get into split radix FFT and then we'll talk about other things about FFT. And then we'll get into real FFT. Okay, so see you next class.
Oh, yes.
Yes, go ahead.
Is the homework turned in on Canvas, or are we turned it in?
No, you turn it in here. I want you to come to class. I want you to, this is no longer remote. We did have links to upload during the COVID time, and I don't want to treat this as a remote class anymore. Unless somebody has very urgent reasons, I may be willing to consider. But you have to send me email and talk about that.